Welcome to Physics 30 Prep Fast Track, Lesson 2.2. We'll look at forces, Newton's laws, and some sample problems. So the second law can be combined with the kinematic formulas to solve for any unknown, and sometimes Newton's first and third laws help to determine the net force. So you can see we have our four basic kinematic expressions at the top, and then below that we have our standard constant velocity formula and Newton's second law, and sometimes we might need g is equal to 9.81. All of these formulas would be on a formula sheet that you would use to help you to work through an exam or quiz or set of problems. So the first problem that we'll look at is a simple example. A ball with a mass of 2.5 kilograms is pushed with a force net force of 50 newtons. The ball was initially at rest. What's the acceleration? For that we can use Newton's second law. Once we know what the acceleration is, then given the time of 2.2 seconds, what's the final speed and how far did it travel? So we're combining Newton's second law with our kinematic expressions from earlier. We know that, of course, since the mass is 2.5 and the net force is 50 newtons, then we can calculate the acceleration by using Newton's second law, F net over m, 50 over 2.5. The units cancel, kilogram meters per second squared. The kilograms on top cancel the kilograms on the bottom, and we're left with meters per second squared. Now here's a little typo. This should say acceleration, of course, is not meters per second, but meters per second squared. So please be aware of that on any handouts you might have, that the unit for that answer should be in meters per second squared. All right, and that's our acceleration. Okay, now that we know the acceleration, we could use it to solve for the final velocity, given that the acceleration is 20 meters per second squared, the time is 2.2 seconds, the initial velocity is 0. Which equation could we use to solve for final velocity? Well, most likely that first kinematic expression that we derived earlier on, isolate it for Vf. And Vf is equal to Vi plus At, or 0 plus 20 times 2.2. We get a final velocity of 44 meters per second, or a final speed, in this case, of 44 meters per second. So we've fairly quickly been able to use two concepts, Newton's second law to solve for acceleration, and then a simple kinematic solution to solve for the final velocity of this particular ball. The last thing is, how far did the ball travel? And to calculate how far the ball traveled, well, we have all this information. We've been able to figure out the acceleration. The last step is to figure out what the displacement is. And here's our solution. What we did was we took the time, 2.2, the initial velocity of 0, and we used the final velocity in this particular example. Now, we could have used A, but I chose in this particular example to use Vf. I didn't have to, but I chose to use Vf because displacement in the second formula that we derived for you is just equal to the final velocity, or plus the initial divided by 2, or in other words, the average velocity times the time. And the average velocity is just the final, 44, plus 0, divided by 2, 22 times 2.2, gives us a displacement, or a distance in this case, of 48.4 meters. So that's one good solution. Notice we used 3 givens and 1 unknown, and we picked an equation that was appropriate for that. Now, an alternate method would be, instead of using the final velocity, we ignore the final velocity and instead we use the acceleration that we calculated in step A. So acceleration is 20, time is 2.2, initial velocity 0. What's the displacement? Choose a formula from the 4 kinematic expressions, or formulas, that of course has these 3, T, A, and Vi, and also has your unknown. Now in this case, we don't need Vf, So we pick the equation that doesn't have VF. And since the initial velocity was 0, the equation becomes 1/2 AT squared. And here's our 1/2 AT squared. And guess what? We get 48.4 meters. And so we have two different methods, and we end up with the same solution for step C. And so whether you did it using step 3 or whether you did this using step 4, both are perfectly acceptable. All right, another example. This one's a little more of a challenge, but we can do these step by step. A ball with an unknown mass is pushed with a net force of 50 newtons. The ball was initially at rest and accelerated uniformly to 22.4 meters per second in 4.70 seconds. What was the acceleration? So here we're going to use Newton's second law. Because we know first we're probably going to figure out what the acceleration was using kinematics. Then we'll use Newton's second law. All right, so what's going to happen here? To find the acceleration, well, what do we know? Initial velocity was 0. Final velocity was 22.4. The time of travel was 4.7. Those are 3 variables, and of course, whenever you have 3, using those 4 kinematic expressions, you can find the fourth. And this one's pretty straightforward because of time, initial velocity, and final velocity are given. Solving for A, we use our first kinematic expression. VF, 22.4 minus 0, that's the initial, divided by the time, gives us an acceleration of 4.77 meters per second squared. All right, excellent little question. Now that we know the acceleration and we know the net force, we can calculate for the mass. All right, because acceleration is net force over m. That's just Newton's second law. We just rearrange this. Since we know acceleration and we know net force, we can calculate for the mass. Just by rearranging that equation, multiply both sides by m, divide both sides by a, we get m is equal to F net over a. Substitute, and I just changed newtons here to kilogram meters per second squared, which is the equivalent units in our basic form, and the kilograms on the top, the meters per second on the top cancel the meters per second squared on the bottom, and we end up with kilograms. So 10.49 kilograms or 10.5 kilograms is the mass of this ball, so quite a large ball. And now that we've calculated for the acceleration and the mass, we can do the third step, which would be how far did the ball travel. So in other words, what was the displacement or distance? And given this information, there are 2 methods, or actually there are 3 methods that we could use to solve for D. We'll show you 2 of them. Given that we know the time of flight or the time of travel, and we know the initial and final velocities, we could just use that information to solve for D. So we didn't actually have to find the acceleration because we have a formula here, D is equal to VF plus VI over 2 times T, that doesn't require acceleration. So we could have done this right off the bat. Final plus initial divided by 2, that's the average velocity, times the time gives us a displacement of 52.6 meters. So very simple, but what if we did it in another way? Well, we could use the acceleration that we calculated in step A, which was 4.77 meters per second squared. So given that A and T and initial velocity are known, what's the displacement? Different formula, but same result. Since the initial velocity was 0, this term is 0, so D becomes 1/2 AT squared. And D is equal to 1/2 times A times T squared. And we get the same result, 52.6 meters. Now, if they weren't the same for some reason, it would likely be due to the fact that we perhaps made a miscalculation in our acceleration. And if you're using the wrong acceleration, you'll get a different D if these two D's don't agree, then somewhere there's a mistake. But the fact that they agree, that actually verifies that our acceleration is probably correct as well. All right, another example. A football tackling dummy with a mass of 80 kilograms is hit by two players at the same time. One player hits it with a force of 320 newtons north. The other player hits the dummy with a force of 280 newtons west. Now, the situation is that there are two forces acting on this tackling dummy. One is going north and the other one is going west. So at the point of impact up here, of course, the tackling dummy is being forced both up and to the west, so it should probably go towards the northwest. Now, to do this kind of problem, we should use a vector diagram. The two forces act as shown on the left, but we should, when you're doing this type of problem, you should add the vectors tip to tail. The first vector is 320 newtons. The second vector, the force vector, is being added to the first and therefore should be added in this way. You take the first vector, add the second vector from the end of the first. And of course, as you can see, these are the two arms of a right angle triangle, and you can find the resultant force, or the net force, by drawing a line from the start point to the finish point. This is called the resultant force, or another name for the resultant is the net force. So whatever that works out to be using Pythagoras, all right, with the diagram complete, you can use Pythagoras to find the size of the net force. And then, of course, if you know the net force and you know the mass, which you do know, then you can calculate the acceleration. Once you know the acceleration, then you can calculate the perhaps the final velocity or the initial, or the the displacement. All kinds of factors can be found. But what's the net force? Well, we'll figure that out now that we have the solution sort of set up. We can go through the mathematics of that. So, putting these two together, we find that the resultant force is c squared equals a squared plus b squared, or you could say the resultant force squared is equal to the initial force, or the first force squared plus the second force squared. But remember, you can't just add 320 plus 280. This is a common mistake that students make. They just go 320 plus 280 equals 600. And it doesn't, because they're not being added linearly. They're being added at an angle, and therefore we have to consider the two-dimensional mathematics. And so we end up with 18088 or 800 as our FR squared, and of course the resultant force ends up being equal to only 425 newtons, which is a far cry from the 600 that you would get if you added these two in a linear way. So now that we know the magnitude of the force, of course we could calculate the acceleration. And we can also figure out the direction of the force, because of course force is a vector. When you're asked for the force acting on an object, you not only have to give the magnitude, but you also need to give the direction, unless they say otherwise, all right? Unless they give you information that would say, don't worry about the direction. Now, to find the direction, you need to use the sine, cosine, or tan. In this case, we could use the tan because we have opposite over adjacent. And, of course, opposite over adjacent is the tangent function. So 280 divided by 320. And if you find the actual angle itself, it's 41.2 degrees. So we know the magnitude of the force, and we also know the direction of the force. So the direction is 41.2 degrees west of north. Now we can find the acceleration. All right, the acceleration is found using Newton's second law. And of course, Newton's second law says that A is equal to F net over m. The net force, as we determined using Pythagoras, was 425. Divide that by the mass of the tackling dummy, which was 80 kilograms, and we get an acceleration of 5.31 meters per second squared. That means the tackling dummy will initially accelerate at 5.31 meters per second squared, and the angle will be west of north, because of course the first tackler was going north, the second tackler was going west, and so we end up going in a sort of northwesterly direction. Now, it's a little more north than west because the 320 is a little bigger than the 280, and so we end up going 41 degrees or 41.2 degrees west of north. Now, we could also give this answer in terms of, so many degrees north of west, but this is a good response to this particular question. Now, just to tie things up, in this particular example, most of the problems you will be asked to solve are of this type, where you're given enough information, either force-wise, you could give an applied and a frictional force, or you could be given a net force, you'll be given the mass of an object, you can calculate the acceleration, you're given the initial velocity, or the final, or time, or displacement, or acceleration, and you use all these in conjunction with each other. And of course, there's lots of different strategies that you want to develop, and one is drawing sketches or pictures. They really help, and try not to do that in your head. Start making marks on your paper and understanding the relationships, and look at your formula sheet, use it a lot until you become very familiar with these formulas. These formulas are given to you, as I said, on a formula sheet. In any physics course, you're given the basic formulas that you need to do the job. And then, through practice, you learn a little bit by trial and error and a little bit by succeeding in these problems. As you succeed and as you learn from your mistakes, sometimes you get better. All right? So attempt as many of the problems assigned in the course. So in the WebCT version of this course, you will see that there is going to be an assignment from the textbook or the workbook that you are working on. You need to do lots and lots and lots of these so you become familiar. Then you can try the quizzes and the other assignments and see how you're doing. But before you actually take a test, you should do lots of practice. All right?